Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the director of content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
I just returned from a long trip in Europe where I was attending some summer schools and conferences, but the best part was that I was visiting a professor at Cambridge named Marcello Fiore. He's a very smart, very nice guy, and we had a really good time starting some potential projects together and mostly me learning from him. Basically, he has this big project that he's been working on for over 2 decades now called abstract syntax, or one could also call it algebraic type theory. And in some ways, it's like a big theory of theories, but one could say more precisely that it's trying to give the algebraic foundations of formal languages. The basic idea is that a traditional algebraic theory, so I think we've talked about these in past RChain podcasts. So for example, the theory of a monoid. There's this nice idea in category theory where we can abstract algebraic notions that were associated with sets. And we can say, oh, all we really mean by, where before we would say that a monoid is a set equipped with a binary operation and an identity such that it's associative and unital. Category theory lets us recognize when we have hybrid structures and we just have some object in the category that has a binary operation and an identity such that it's associative and unital. So you could have something that's a space that also has some kind of algebraic structure. And this is very useful for a lot of purposes and lets you use this philosophy called internalization. So you can recognize, you can look at some complicated definition and then you realize, oh, it's just a blank in blank. It's like it's a monoid internal to cat or something. There's a basic limitation to these theories. So ideally, we want to give algebraic foundations to programming languages, and in particular, the process calculi that we're going to be using in RChain. But as it stands, you can't sit down and write down a theory of the row calculus or a theory of the pi calculus in this sense of a theory. And the reason why is that these kind of categories lack a notion of variable binding. When you write, for example, the input, so the input operation in the row calculus is the one which binds a variable. So when you say 4 and then X, arrow A, you're listening on channel A and receiving something that you're going to call X. And then in the continuation P, you're going to do something with that X. But the point is that X in your notation is just a placeholder. It only has meaning relative to this expression. And the basic rewrite or reduction of the row calculus or the pi calculus is substitution into an input. So if you're inputting on channel A and in parallel someone is sending on channel A, in the row calculus, these would be names of or quotes of processes. Then the data, the process which is being sent, and channel A is communicated across, and it's substituted for that distinguished bound variable x. And then the continuation starts with whatever was substituted. And that's the subtle thing that you cannot express with normal algebra. There's a similar problem in the lambda calculus in the foundations of normal functional programming. When you write lambda x dot x plus x and you want to apply it to 2, you're going to substitute the 2 in for the x and get 2 plus 2. But the idea is that an operation which binds a variable in this way and makes this distinguished placeholder that you intend to substitute, that's a different kind of operation than any of these in-ary ones. So basically, about 20 years ago, Marcelo Fiore and Gordon Plotkin and Danielle Turi wrote this paper called Abstract Syntax with Variable Binding. And it essentially solves this problem. It lifts normal algebra from normal categories called Levere theories up into functor categories. And the idea is that, like, the category of functors and natural transformations between them, when you fix two categories, this contains a lot of really rich structure in which you can do all of the normal algebra that you did before, but you're capable of expressing a lot of stuff that you couldn't before. And that's what I came to Cambridge to learn from him. And I've learned a lot, and I feel like I now have the right tools to sit down and write an actual enriched typed theory of the row calculus, and start to give the full algebraic foundations. But first, let me just pause for any questions or comments.
Yeah, so thanks for that. That's a nice characterization. I think we should mention that, when you say that there isn't a theory, you mean one of these algebraic theories or higher order abstract algebraic theories that represents and that sort of satisfies an internalization criteria. There are a few other subtleties. One is that Fiore's syntax doesn't actually account for the rewrites. When you talk about a monoid has no unidirectional rewrites. It has only bidirectional rewrites.
Yes. So this is one of these things where he has he's worked out how it works, but he hasn't published it.
Right. Yeah. And you've been looking at graph enrichment as a particular approach.
Mm-hmm.
People have looked at this extensively. Plotkin's SOS rules as a format for expressing rewrites are very successful. But to the best of my knowledge, there isn't a consensus on a rule format that is, widely accepted by the community as capturing all the things that we want to be able to capture. This is actually a point I was talking to Mike about, because the graph enrichment it's a nice tool, but it doesn't articulate all the structure that these rule formats articulate. And sort of getting a handle on all of that sort of fine-grained structure is important, especially if you're someone who actually is designing a language, right? Because whether you're talking about the transitions in the Java virtual machine or, just the rewrite rules of the ambient calculus, there are a lot of interesting cases to cover. And so you need some fine-grained structure to be able to articulate those cases in a way that sort of economically specifies the language. And that leads me to a question. Has Marcelo tried this for the ambient calculus? Because the ambient calculus is not substitution based. It's a very interesting puzzle.
I'm not sure if he's done it for the ambient calculus, but yeah, I know he's done it for the pi calculus.
So if you recall, you and Mike and I were looking at sort of two issues. One is making the Hom set be a collection of the type of collection that we were, in the distributive case. So in other words, the HOM set is enriched in that way. And the other is the HOM set is enriched in the rewrite rules. And we were curious about how those two enrichments might interact. And then Mike had an alternative proposal where you encode the theory of the graph, the rewrite part of the structure, as a theory, so which would then separate the two, right? The enrichment would be in terms of the collection, and then the graph part would be added in as an additional theory. And the thing that speaks for that approach is that the source and target equations become a language, a more fine-grained language for your rule formats.
Yeah.
The final point that's of interest is that the types that you end up with are not related directly to either the types that we get from the chi-race style formulae, as in spatial behavioral logics, nor are they like the session types. These are categorical types, and their expressiveness with respect to concurrency is yet to be explored. It will be interesting. The point of the Ladle program is to provide an underpinning for explaining both the chi-race and session types and showing how there's something underneath them that does the work. And one of the interesting success stories there is that you can unify the arrow type of the simply typed lambda calculus with the Hennessy-Milner modal. I'm curious, what have you done with respect to the investigation of the types?
I was kind of hoping to explain the idea of the research first.
Oh yeah, go for it.
Isaac, did you have any questions?
Oh, I just wanted to maybe hear a little bit more as to how this variable binding idea differs from these, arity operators. If you could just say a little bit more about that, that'd be great.
Yeah, sure. The idea is that we have a category of contexts in like the type theory sense. So if you've ever seen these judgments where in the hypothesis you have these terms of these types, then you can deduce these terms of this type. So the first half is called the context. So it's your current place in your reasoning that you are.
Yeah, so like type environment, is that kind of what you're talking about? Okay.
Yeah, exactly. So the idea is that we have a category of context.
Mm-hmm.
The objects in there are types.
Okay.
And if you take like a product of a bunch of them, that's another object that represents having, one of each of those, one term of each of those types. And so what we want to do is think about functors from the category of context back into sets, or when we start enriching, it's going to be our enriching category.
Okay.
But the idea is that a functor from the category of context to sets. So let's just take the category to be finite sets.
Mm-hmm.
Then this takes in just the finite set n as kind of the generic invariable context, and gives you the set of all terms in some language that you could form with those invariables. So a functor like capital lambda from finite sets to sets. For every natural number, it's telling you for natural number n the set of terms in the lambda calculus that you can form with n free variables. And so it's describing like the stratification of the language by, like, if you imagine the process of generating a language. So the lambda calculus is generated by variables, application, and abstraction. When you specify these as these judgment rules, they depend on the context. So the one for variables is really easy. if you're in the context of n free variables, you can just project any one of them, and you can have x sub I. For application, if you have in context n, you can derive term t1, and in context n, you can derive term t2. Then in context n, you can derive their application to each other. So those two are easy, but the one that's doing something interesting is lambda abstraction, because it's binding a variable. So the way that you write this is that if you're in context n plus 1, and you can derive term t, then in context n, you strip away that distinguished plus 1. You can derive lambda x sub n plus 1 dot t. And so this brings you from a higher level of n plus 1 context back down to the context of n, and you've plucked that distinguished plus 1 and turned it into a distinguished bound variable. It was free on top, and then it became bound on bottom.
That makes sense.
So the functor is keeping track of these levels, and at any level it can tell you exactly which variables are bound versus free.
And functoriality is guaranteeing what?
It's guaranteeing that these terms are stable under renaming.
Yes.
So morphisms in the category of context are just renaming variables, shuffling them around. You could, since we're in a Cartesian category, the extra structure we have is that you can duplicate variables or delete them. If you ever want to be in type theory where you don't want to be able to do that, so in linear type theories, then you change the category of context to the category of finite sets and bijections rather than any functions. So you can only shuffle variables around.
So the functoriality is basically playing the role of alpha congruence. Is that what you're saying?
Yes. Yes.
Okay.
That's right.
Yeah, and that's one of the things that makes this theory appealing, at least from a computer scientist point of view, right? Because people who came up with the notion of functoriality were not thinking about alpha congruence, right? And the fact that alpha congruence suddenly, or functoriality suddenly explains alpha congruence. It's a point in favor of this approach.
Yeah. Basically what's going on here is that in addition to normal, like in-array operations, we now have this new kind of arity, which is secretly an arity of a certain functor from finite sets to sets. It's the inclusion of finite sets into sets. It's called like the presheaf of variables. And when you take in this as like an arity of an operation, rather than just taking in a certain number of things of certain types, you're actually taking in a distinguished free variable. So the lambda abstraction is an operation from delta. It's called a lowercase delta of capital lambda to lambda. So it takes in a lambda term plus one distinguished free variable and gives you another lambda term where it's now bound. And so this is kind of the key difference that lets you start talking about the formal languages that logicians and computer scientists really care about, because substitution is, the heart of computation, and it depends on the notion of variable binding. Basically, you lift normal algebra to these categories of functors on categories of context. Yeah, you can do everything that you could before, except you now have this variable binding.
And by the way, we should give a little bit of provenance. So while yes, Fiore et al. Worked this out in this setting, the original intuition came from John Reynolds, who was attempting to explain reference semantics in ML. Right, so he wanted to be able to keep a variable state where you can grow or shrink reference locations in the environment, right? So like if you don't have any mutable state in your environment, you can handle this in other ways. But when you do have mutable state, which is roughly, on par, pun gratefully accepted, with the new construction in the pi calculus, then you need a different story. And so he proposed the functor categories to model those semantics. And so this idea has been floating around for a good 40 years, I think, and was adapted and made prettier and cleaner. But the idea has been around for a while.
Yeah, I don't know much about that program of Reynolds. So Isaac, did that kind of make sense?
Yeah, definitely. Yeah, thank you for the additional explanation.
Yeah, I would love to. It was great last summer when we were doing that little online class about topics in our chain. I would love to talk about this stuff there. It's really beautiful stuff. So that was the basic idea that Fiore et al. Outlined in a 1999 paper. And since then, the project has been built up more and more, so that the basic idea with functors on finite sets to sets has to do with untyped or one-typed languages with Cartesian context. The category of finite sets, or technically its opposite category, is like the free category with finite products on just one, the terminal category. So in this, you can only express, for example, the untyped lambda calculus. So for example, the way that you could start getting types involved is that instead of just taking that free construction on just the one object category, you could take it on some set of types. So basically, if you do the same thing, except your category of context is pairs of natural numbers, then the slots of the tuple represent that you now have two types. And if you do the same thing where you're taking functors on this, now your context says, okay, you have three of the first type and four terms of the second type, for example. But the subtlety about the row calculus is that you don't just have two types that are existing in parallel. You have these reference and dereference operators that turn the types into each other, or sorts, if Greg would prefer the term sorts. What would you call the distinction between names and processes, Greg?
And normally those would be called sorts. But yeah, I understand it. In the categorical semantics, you call them types. But
Yeah.
Yeah, in the computer science world, those are sorts.
So in this case, there's going to be more structure rather than just taking like the free category rather than just doing some kind of, yeah, sorry, if you've never heard of the term free, basically it means that you generate some kind of structure where you don't impose any extra rules. So if you want to take some alphabet and form the free monoid on it, then what you're doing is that you make a set of all words that you can form in that alphabet, plus an operation that's just like putting words together. And this is called free because it's kind of like the simplest possible monoid structure that you can put on a set, on that set. So similarly here, we start out with some initial data.
Do you mind if I interrupt for just 1 second? So I mean, the way I think about free versus other structures is that free has no equations, whereas other monoids might exhibit some equations. For example, commutativity or idempotence.
So it still technically has the equation of associativity, but it doesn't have any extra equation.
No extra equations. Yeah, exactly. I mean, in general, if we're not talking about monoids, but we're talking about just arbitrary algebraic structures, there's free means no equations. In the case of monoids, you have to have at least the associativity and identity equations. You know, it's useful for people who are thinking about this is when you add equations, you're erasing structure. Free has all the fine-grained structure, and as you get more and more equationally constrained, structure gets erased or identified.
So for example, this isn't really how it's going to work, but it's kind of an approximation. Instead of just having a set of types, what we're doing is that we would start with this small little category that just has one object for names and one object for processes. And then these two arrows, one going from process to name and one going from name to process, such that certain equations hold. This isn't the full story because you won't quite be able to express communication on that level. But the point is, like, instead of just taking a free category on some set of types, the sorts in the row calculus have this much richer structure, and they're already kind of intrinsically related. So even just properly stating the theory of the row calculus in this framework is going to be a very interesting paper, and incorporating the enrichment might even be a whole paper on top of that. Right now, it's kind of hard to judge exactly how difficult it's going to be. But yeah, I'm really looking forward to it because the row calculus brings in some new ideas, most of all reflection, that has never been considered in this abstract syntax framework. And I think it'll add some really interesting new dimensions to those ideas.
That's cool. Can you give us some thoughts? I mean, have you gone down the rabbit hole a little bit to tell us whether or not there are any dragons or red queens down that rabbit hole?
Basically, unfortunately, no, not really yet, because I've just gotten back from these trips. Fiore and I spent 2 weeks together in at the beginning of July or the end of June. But since then, I've been at these conferences and summer schools. But yeah, I mean, he thinks the notion of reflection is really interesting. He's certainly willing to help us work on it.
Oh, good. Did you have a chance to show him the space-time calculus, where you don't just reify processes as names, but you reify contexts as well? Now here we're talking about term context as opposed to type context.
No, sorry, no, I didn't show him that.
That's okay. It's no big deal. I mean, it's you know, reflection is already, it's a big step for the community.
Yeah.
As I continue to find out.
It's brand new to almost everybody. Like, he's really integrated into this high-level research community, so informing him about this stuff is going to be really useful.
The computer science community doesn't understand the utility of namespaces yet. Back in 2005, when I was at the Trustworthy Global Computing satellite of ETAPS, you know, I just began to touch on the idea of namespaces, and I gave them a few examples, but then I sort of withdrew from that community in order to go after biology. Well, I mean, we do on a regular basis partition namespaces because that's what URLs do. But the more you can do this in an abstract way, where you can logically characterize the namespaces, the more power you get in terms of being able to reason about the end-to-end behavior of the system, such as being able to build compile time firewalls and these kinds of things. I think the community has not yet internalized the power of namespaces. I mean, I'm still just coming to grips with them, you know, as the results on the reaction rates, encoding reaction rates via namespaces. That was a shock and a surprise to me. I did not I did not see that coming. it is a big step, and the computer science community proceeds in a deliberate pace.
Yeah.
Well, I guess I'm really excited to see where all of this stuff goes, because yeah, I've been looking into namespace logic a lot recently, and kind of all of the things surrounding that stuff, all the behavioral spatial types. Um, so yeah, I'm really interested to see where this research that you're doing ends up.
Regarding the namespace logic, when I was showing it to Marcelo towards the end of my stay there, he was looking at this interpretation. If you go to the
Mhm.
namespace logic paper, there's the page where it just lays out the interpretation of all the row calculus operators, but then also you're augmenting the signature with some logical operators, and that's how we're getting more expressiveness on our types. The interpretation of the logical operators is pretty straightforward. I mean, like and corresponds to intersection, or
Right.
corresponds to union, etc.
Mhm.
But the ones that are kind of doing the hard work is the interpretation of par, for example.
Mhm.
In order to split an atom like that, you need to be able to consider all possible pairs of processes, such
Mhm.
that when they're put in parallel, they act bisimilarly to the process that you're interpreting.
No, not bisimilar.
Oh, sorry, structurally equivalent. Yeah,
Structurally equivalent. Yeah, there's a big
yeah,
difference.
yeah. Sorry. It was really interesting. When he saw that, this is one of the advantages of just being like hyper educated. He said, "Oh, that looks like this thing in category theory called the day tensor product." And we started to work it out, and it actually is this date. It's basically if you have some monoidal structure on a category.
Mhm.
So, for example, you're thinking about par as an operation on types, where these are um, these terms in the namespace logic are being considered as the types. This gives you a way to lift that monoidal structure to a monoidal structure on the category of functors on that category. So if here we're thinking about all of these terms in the namespace logic as being types or objects in the category of context, and the operations are giving us operations on that category, they're going to lift to the category of functors on that category. And it's not definite yet, but it's looking like this may give an automatic way to naturally split apart operations. So not just the par, but any of these binary or in-area operations on types. So there's a chance that this could give a streamlined way to generate these interpretation functions, where if you have a signature for a certain process calculus, and then you augment it with the signature of a certain kind of logic that you want to add to it. It's not definite yet, but it's very tantalizing right now how it looks.
What did you say the categorical construct is called?
It's called day convolution. So the in-lab article about it might be difficult, but basically just picture like, so are you kind of comfortable thinking about a monoidal structure on a category?
Yeah, I think so.
Okay, cool. Yeah. So it's basically like the simplest way if you're considering, I keep saying functors, but we're really talking about presheaves on the category of context. It's the simplest way
Okay.
of lifting the monoidal structure on the category of context to the category of presheaves. So if down in the category of context, those are our types. The presheaves are like
Mm.
the languages that are typed in that way. So we're lifting um, those operations on the types to the operations on the languages themselves, to terms in the language.
Of the things that you and Marcelo have talked about, the day convolution is the one that's really interesting to me. I've long thought that there ought to be a role for day convolution in this setting, and so if it turns out that that we can make that work, and it sort of gives us a better sense of how, what makes all of this tick. That would be great news.
If you read that formula for like the interpretation of P par Q.
You mean phi par C?
Sorry, yeah. It's saying all, was it R?
I usually use M to go after the terms. So you take the total language, right, the set of all terms, and you find all the M in them such that it decomposes into an M1 par and M2, right? So it's structurally equivalent to an M1 par and M2. And M1 satisfies phi and M2 satisfies C.
Yeah, exactly. There exists M1, comma M2 such that M1 par M2 is equivalent to M.
Yeah.
That's precisely the formula for day convolution. There's this thing called coend. It's actually a decategorification of day convolution.
Very interesting.
Yeah, there's this certain kind of universal construction in category theory called end and coend. They're like limits and co-limits that understand variance. And the co one is like a really fancy there exists. It's actually a big generalization of the existential quantifier. Yeah, so you're saying coend over all types. You're checking for other types because these could be other objects in your category of context, which are terms in the namespace logic. It would be easier with paper, but it's literally a translation of that formula, and that's why he kind of lit up when he saw it and said, "Oh, that's the tensor product."
Wow, that's really, really cool.
I think it's a big hint at something. So that's what I'm going to be. In addition to, that's the thing, is that I think that even to do the theory of the real calculus right with the right kind of types in this framework, you have to have already figured out Ladle. Because if we really do want Ladle to give us the types, then from the very beginning, we're going to have to be describing, taking functors on whatever this category of types is like. I think we might have to figure out the same time as the theory.
I think you're probably correct. And one of the things that I've been most interested in is, so Samson Abramsky described these interaction categories. So, and if you look at the way he, what the types are and how he generates the category, there's this big, wide open invitation. Can you take the Kairos types or the session types or something that's sitting underneath them and build the category where the types are the objects and the morphisms are the computations? That's the really interesting question, and so far no one has done it.
Which paper is that?
If you just Google interaction categories, there's just a bunch of papers. He and Simon Gay and Raja and Guy McCusker all looked at various instantiations. So in Samson's, at least one incarnation of the ontology that Samson was sketching out, interaction categories was the foundation. And then the game semantics was an instance of interaction categories. And CCS, they could give a type system for CCS, they couldn't do pi. The CCS was another instance of interaction categories, but interaction categories was the overarching construction. And Mike and I are getting awfully close to that territory again, because we've been looking at session types, and they're, spurred on by the no-go theorems. The types can only have certain shapes. And then Mike said, well, but what about session types where they don't have that shape? And then we looked carefully at that, and it turns out that they do. It's just that the way you handle negation is now folded into execution. And that's not the case with the Kairos types. The Kairos types, the negation is all about the collection. But in the session types work, or at least the Abramsky flavor of session types, the negation is mutually defined in terms of cut, and which is the execution operation. So again, you recover this foundational structure. So we're getting awfully close to the territory you're talking about. So it might be a good idea for you and Mike and I to talk.